All right, so welcome back. We're going to continue our discussion by looking at MATLAB script of steepest descent algorithm. We look at an example with objective function of x minus 3 raised to the second power plus 3 times y minus 1 raised to the second power plus 2. Okay, so we plotted the functions and we look at the top view of the control lines, which we can look again. So this is the control, well, these are the control lines, the minimum right here, and the initial guess is somewhere around this point, I believe. It's actually supposed to, yeah, so, okay. So this was the top view, this is the side view, so you can see that it's a bowl shape, and the minimum is somewhere around here. Okay. So the way we write the function is we use the inline form. We're going to call a function called func, and this func requires a couple of arguments. The first thing is the objective function itself, so from here to here. Okay, this whole thing is objective function, is a function of x. And now for x and y, we're going to have x1 and x2, the first and second component of x vector right here. The second argument here is the derivative of the objective function, which is the gradient of it. Okay, so it's going to be a vector, that's why we have these two brackets. And there's also a function of x, which means x1 and x2. So the first element of x, so the first element of the gradient, and this is the second element of the gradient. And if you remember, we're talking about the gradient of f, which is this, so 2x minus 1 minus 3, and then 2x2 minus 1. And that's the same thing here. So 2x x1 minus 3 and then 6x2 minus 1. Right, so up to here we calculate the gradient of f as well. The next is we're going to give the Hessian matrix. And the Hessian matrix is, well, in this case it's not a function of x, but we can just in general have it as a function of x. Okay, the Hessian is 2006, which is the Hessian matrix we calculated is let me see, Hessian matrix for, yeah, so it's 2006. Well, Hessian matrix is not required for steepest descent direction, I believe. So for steepest descent direction, oh, actually we do need, yes, we do need the Hessian matrix, that's right. Because this is required to calculate phi prime of lambda equals 0. Okay, so that's the Hessian matrix, and then the initial guess, number of, or maximum number of iterations, and then the threshold. So we pass all these arguments to the function func, which we're going to see next. So this is function func. The first element is just the function, the objective function f. The next is the gradient of f, then the Hessian of f, initial guess, maximum iteration, and epsilon. The same thing we entered there, we're going to receive right here. Okay, so immediately after we receive these values, we're going to plot the guess value x naught and 1 and x naught 1 and x naught 2 as a red dot on the curve. And if I put this point right here, you can see that this is the initial guess right here, 0, 0. Okay, so now we're going to calculate the steepest descent direction, which is the negative of the gradient. Now we have the gradient. Upon x naught divided by normal bit. So we normalize it to make it unit length. Initially we make another guess for lambda. Let's say lambda initially is 0.1. Then within this algorithm, within this step, we have to call Newton's method to calculate lambda. So this is basically the call to Newton's method. We say, okay, lambda is going to be the output of this function phi func. Okay, now phi func is function of lambda, so we have to pass in the function, the objective function is a function of lambda, so it's f of x naught plus lambda, exactly what I had in the notes. Then you have to have the derivative of this, which is the r prime or r transpose, times the gradient of f at the same point. And then we also need to pass in the second derivative, which is the r transpose Hessian and then r. So this thing is exactly right, so I'm passing phi lambda, phi prime lambda, and phi double prime lambda. We pass these three all into the argument list. So this is phi lambda, phi prime lambda, and phi double prime lambda. We have to pass in the initial guess for lambda, maximum iterations for lambda, and epsilon for lambda. And then we're going to plot, as soon as we get back the result from lambda, we can update our x1, and we can just plot x1 on the same chart. So now let's look at this function phi func. So here's phi func down here. So the phi func actually takes phi prime, phi double prime, lambda naught, maximum iteration, and epsilon. He creates a table for us to see how lambda is progressing. Okay, we just do the Newton's method on lambda. So initially lambda is going to be lambda naught minus phi prime lambda naught divided by phi double prime. That's exactly this equation, right? So lambda is equal to lambda naught minus phi prime over phi double prime. That's right here. Then we just pass this into a loop and check if the lambda and lambda naught are close. So lambda naught, if this is bigger than epsilon. So this is a little bit different than, well, actually it's the same as this here. Lambda minus lambda naught bigger than epsilon. I have the same thing here. So lambda minus lambda naught bigger than epsilon. And then also the maximum iteration count has to be less than the maximum number of iterations. Okay, we get the lambda naught updated using Newton's method right here. Okay, so this is new lambda is equal to O lambda minus phi prime lambda divided by phi double prime lambda. We print out the result for the number of iterations for lambda, lambda itself, phi lambda, phi double prime lambda. Once this loop is converging, or once it has converged, then we know what the lambda is. We bring the lambda back to the loop over x. So now we have lambda, we're going to update our x. We make a table for x. We're going to print out the number of iterations on x, the gradient of f at point x, the steepest descent direction, which is going to be the negative of the gradient. We're going to print the lambda we found from the lambda loop, and then we print out the next x, and then the function, the objective function evaluated at that point x. And we're going to plot that point also on the top view. So we're going to plot x as well. Okay, and then at the end we're going to check if the number of iterations hit the maximum iterations. We're going to output some error saying that maximum iterations, has reached. Okay, so this check is outside the while loop. So after the while loop ends, we're going to check whether we hit the maximum iterations because we know how many times we iterate. So this key actually counts how many times we iterated in this while loop. All right, so now if I continue doing this, first of all, you see that the path is zigzag, and if I zoom in here further, you see that still is a zigzag. So it goes all the way as a zigzag pattern to the end solution. So look at the scale here, it's getting very, very close to 1. And you see that the zigzag pattern still persists. You see the zigzag pattern here? All right, so zigzag pattern is all down to even very, very fine scales. Okay, now let's look at the output here. The output, first it's the iteration over lambda. So this is a table for lambda. Okay, so the first time we approach this, our lambda actually converged very fast in the first iteration. The second time around, yeah, still lambda converged in the first iteration. Then we go to, well, actually this has to be alternatively. This has to be very, well, the table for lambda and x should be alternative, like we get a table for x, then we get a table for lambda. Then we get a table for x, another table for lambda. So it's table for x lambda, like that. So that's what we have here. This is a table for x, this is a table for lambda. Again, table for x, and then table for lambda. And then table for x, and then table for lambda, and so forth. So let's look at the table for x first. So first it says the number of iteration, the negative of the gradient, which is a vector. You see that 2 elements here. And then r, which is the reverse of that, normalized. So this is the negative of the gradient normalized. And then we have lambda corresponding to the first step. The x corresponding to this lambda. And then the function, the objective function evaluated at this x. Then we go to, well, I think And this might be the next lambda, for which we use this x. So this is again another table for x, same pattern, same format, but this time we're going to use this lambda. Okay, so in lambda table we have the number of iteration over lambda, lambda itself, phi prime lambda, phi double prime lambda. So the goal is actually at every iteration the phi prime lambda should go to 0, because that's the root of phi prime lambda, and that's how we can find lambda. So lambda is supposed to be when the phi prime equal to 0, which means phi lambda, which is nothing but the objective function, is minimum. So again, phi lambda is equal to f, and if you want to minimize f, which means we want to minimize phi, which means we have to set the phi prime to 0. So the convergence on lambda is justified when the phi prime lambda equal to 0. Okay, so and then next step, same thing. Always phi prime lambda has to be 0, otherwise the lambda we're going to use is not a good lambda, it's not an accurate lambda. Okay, so at the end of the day, it goes through something about 20 iterations in x. Okay, and the result is going to be 3 and 1. So the minimum is going to happen at point x equal to 3 and y equal to 1, and the function at that minimum is going to be 2. Okay, so this actually was this was about how you can write steepest descent in MATLAB. In the next video, I'm going to show you the algorithm to write Newton's method to avoid basically the zigzag pattern we saw here. So again, the issue with the steepest descent is, the zigzag pattern sometimes takes, a lot of steps to converge. So the question is, can we basically get the minimum faster than steepest descent? Okay, so thank you so much for watching. Stay tuned for the next video on Newton's method to minimize an objective function.